Alright guys, so I want to show you how we can speed up our volume simulations or smoke simulations by optimizing our collisions. So as you can see, this sim volume cached took about 1 minute 25 seconds for 48 frames, and that's me caching out the collider. And you can see the problem with this method, even if I have 3 subs turned on, we could still see some stepping, especially these parts in this frame. So this file cache, which is the rebuild SDF, is basically not caching out our collisions and generating the VDBs on the fly. Making sure that this crag has $FF obviously, so it has some in-between frames. But the problem with this is that it slows our simulation because it has to rebuild the SEF every single frame. So as you can see, from 1 minute to 25 seconds, all the way up to 1 minute 42 seconds. So this is the cached, it's the one rebuild. Now we can take it further by this new method. So this just went up from 1 minute 25 seconds to 1 minute 26 seconds. And as you can see, it solved the stepping issue from the cached version. Look at that. Boom. Pretty cool. So all works out. You have some great looking collision velocities. Okay guys, let's start from scratch and let's talk about how I came to the method I'm using. So essentially it came from a new node called VDB Collider. This node came with Houdini 20.5 and it's used for, I think it's used for mostly for npm solver. So it goes there, and you obviously have your npm container and stuff like that. But the cool thing about this VDB Collider is we can generate a bunch of methods. We can generate SDFs in 3 ways. So we have the static, which is basically giving us 1 frame depending on what frame we set here. So that's going to be a static SDF. Another one is we have the animated rigid, and what this does is we have an SDF, yes, but you can see it's really fast. And why is it fast? It's because under the hood it creates the SDF VDB in 1 frame, in our reference frame. So that's a static one. But then it computes, transforms from our incoming geometry, from our incoming animation, and applies that animation onto our static VDB SDF. That's why it's really fast. And the third method is animated deforming, which you can see it is slow. And why is it slow? It's because it generates the SDF every frame. So it does basically VDB from polygons every frame, yeah? So that's why it's really slow. And what we actually want is the animated rigid. This is the method that we need to optimize our pyro sim, our collisions for our pyro sim. So sure, why not just use VDB Collider? So if you just use the VDB Collider, we obviously can. But normally what a pyro solver would ask for, so under the collisions tab, it usually asks for the SDF and a velocity volume, right? The problem with the VDB Collider under the animate rigid method, we don't get velocities. We don't have any velocity field down here. We get velocity only when we set this to deforming. So if you middle mouse click, we have the velocity 0 here, right? But then if we use the animate deforming, we're not getting the speed that we want. So from 20 FPS all the way to 80, 90 FPS, right? So how are we gonna get velocity volumes from this animated rigid method? So I'll show you how to recreate this method and then plus adding our volume velocities on top of it. Okay, cool. So I'm gonna start off with the test demo that I've been working on to create these statistics. So all I've done is it's the same thing. I just isolated the hammer, converted back to polys, but to increase the complexity, I just sped up the animation by 1.5, so it's a lot faster than it normally is. I think it's glitching. Oh my god. Cool. Okay, so I sped it up, and for my initial volume source, for my density source, I just took the head of the hammer, peaked it out a little bit, and then converted it to a density, a fog volume basically. Okay, cool. And this is just the domain of my pyrosim, just so that I am a lot more efficient with my simulation. So on the pyro solver, under the bounds, I'm setting a maximum size for my domain, and I just have these spare parameters that references the domain and gets the B box and the centroid of that bound. And just copy reference on these guys. And I've set up a global subset of 3 for all of my tests, and under the collision, I'm getting in collision field and the V field from this collision SDF. For my sourcing, I also just have density. I don't have any velocity on my source, so you can see there's no velocity in there. So these don't do anything at all. Under the fields, I'm getting a speed field just so that I could use that as a mask for my turbulence. Nothing too fancy, it's just something to make the simulation look a little bit better for the tests. And I think that's it. There's nothing in there, and I'm just outputting density in the end. Cool. So for my initial tests, this is what we would usually do for our collisions, right? Compute the velocities of our geometry, do the SDF thing. I set it to be a collision name for my SDF and V for my velocity field, for my velocity volume. So now I have collision and V. And I resampled my velocity volume just so that I'm a little bit more optimized, since I don't really need that much detail on my velocity volume. So it's lower resolution, much more lower resolution compared to my collision SDF. And I'm writing it out as 16-bit floats. So that's our typical workflow for collisions, right? And when we would usually cache this out. But yeah, the problem with this method when we cache it out is we don't get those super nice subsets we get from either an alembic source geometry or from our time blending hours setup. Yeah, so that's why we get these steppings, even though we have quite a bit of global substeps on our solver. And then when we don't cache it, we get super nice streaks on our collisions, no more stepping, but we are also increasing our simulation times. That's cool. So we'll try and do this method now, and I will show you how to do it. Okay, so let's take this guy first, our initial geometry, and we'll create a null, and we'll just call this collision geometry, whatever. And we'll do the same thing if we check our VDB Collider node from Houdini, guys. We've got a reference frame, so we'll do something similar. So do a time shift. We time shift it, our collision geometry on the frame that we want to pause everything. So in my case, it's frame 1. Now it's paused. And this is node, this awesome node that I feel like you guys should use it a lot more. It's the extract transform. So we have our reference geometry, which is the one that's static, and our target geometry, which is the one that's animated. And what we want to get, so if I just plug these in, we have a point in the middle of the world. So we got a point down there, and we'll also get some attributes. But what we want is not instancing attributes. We want a full 4x4 transform. So on the extract transform node, we'll change this to transform matrix 4x4. Middle click now, we have a transform 16 float matrix. That's what we want. And our extraction method, we can switch this to uniform TRS, translation, rotation, and uniform scale. If your input geometry has non-uniform scale, it might be bad for your VDBs if we have non-uniform scale. I have never tried it yet though, so just use the uniform scale. Because I know the SDF will probably not complain if it has some uniform scale. Cool. Now we have a full transform, 4x4 transform. And what we want to do, it's currently a point attribute. We can just promote that to into the detail attribute. Awesome. So now that's a detail attribute down there. Cool. So first things first, let's convert this geometry now into our SDF. So we'll just put it to 0.005 just so that we get the super nice shapes. And I'm gonna fill interior just because my source is basically the whole thing. And I just want to call anything inside of the hammer. So I'm going to fill interior, and that's awesome. So now we have the detail attribute now, the transform. What we can do, we can copy that attribute. So it's on the detail attribute, and that says transform. So now our transform attribute is now on our VDB. Now we can use the magic node, transform by attribute. And this node is awesome because now we can apply our animation to our static VDB. Isn't that really cool? So I'm just going to template our collision geometry. You can see it there. It's following it perfectly. Awesome. So now when our problem was basically we're just following the VDB collider at this point. So we have animated rigid and we have a surface field. And here we also have a surface field, an SDF. But remember, what we want is actually the surface, the SDF, and a velocity field. So how are we gonna get the velocity field? So first of all, let's create that velocity field first. Obviously, we could create it here. We could, well, I have this node, volume extra fields. We can obviously do it this way. So I'm gonna say surface, and then vel. It's gonna be a vector field. So we can do it this way. So I'm just copying. Inside this HDA is just a for loop, because we can create multiple extra fields. And I just want to create a vel field, a vector field, and reference the surface for my active voxels. We can do it this way, but then remember, what we want is to not build VDBs on the fly. We want to build our VDBs on a static frame and then apply our transforms, our animation on that static VDB. So we're not going to do it this way. So what we want is, we actually want our VDB to be initialized on the reference frame. So how are we going to do that? So let's create a VDB node, and that would be our val node, sorry, our val field, and the type will be vector float. And set this to displacement, velocity, acceleration. Okay, so next is we want to activate the voxels of this guy. So VDB activate, and we will activate it based on our surface field, our SDF field. Cool. So VDB activate, set it to reference, and activate using VDBs. Now we have a new field, and you can see it's clearly there, but this will initialize our val field with a value, and we don't want that value. So we can just turn this off. So now we don't see it because there's no values in our val field. Okay, cool. Next, just as an added control, we will add this VDB resample in case we need to optimize our thing further. So I would set it at a default of 2, and that's all cool. And now we can, so another thing I want to do as well is just making this invisible so that the viewport wouldn't slow down because of, you know, the fields. So just put down a primitive node, and under volume, adjusted visualization, and we'll set it to invisible, sorry. And then we'll also write out 16-bit floats, because why not? Merge that with our VDB, SDF, and now we have surface and vel. Perfect. Now we can transform that. Boom, we have the super fast benefits. But do we have any information on our velocity field? Let us see. So I'm going to move to a frame where there would be some velocities. I'm going to check, let's scatter some points, and then volume trail. Hello, excuse me. Where is the velocity? So as you can see, there's nothing. Why is there nothing? Obviously because we have set our velocities to 0 here. Let's put it to 1, we'll see something, but it's obviously wrong. Look at that. That's wrong. So this is not what we want. So what we need to do next is compute our own velocities, our own values. Okay, so before we proceed, before we try and compute the velocity values for our vector field, for our velocity field, let's see our like the usual logic on how we would normally compute velocity vectors by from normal geometries. Okay, so I'm just gonna put a sphere down here and then just add a mountain top with some animation on it, and let's just see the speed. Okay, maybe a little bit faster. Awesome. So normally when we want to compute some velocity vectors, we will just compare the current frame to the frame before, the positions. So on the side here, I'm just gonna put a time shift node down and do a $f -1, which just basically means the frame before, and plug that into our second input of the attribute wrangle. Okay, so what we want to do is we want to fetch the position on the frame before, which is previous frame pause, and we just get the position, and we can use the point number because it's literally the same geometry, so the point order is all consistent. And next we want to do our velocities, and we get our current position minus the position of the frame before, and we're just going to multiply this by 24, the seconds basically. And now what we can see, I'm just gonna put an add node down. So what we can see now is some velocity vectors, which is pretty cool. So now it actually has some velocities. So this is typically known as calculating the backward difference. So on the trails hop, you would see when you want to compute velocity, you would have this velocity approximation. And by default, it says backward difference. So this is essentially the most basic logic of it. If you put down a volume wrangle, we don't have access to point or all that jazz. We do have a volume sample, but we're not sampling the values of the volume. We want to sample. We essentially want to get the position of our incoming geometry and the geometry that is before the current frame. So in the volume context, we have these things called voxel index coordinates, and in the volume wrangle or in the volume VOP, I just want to quickly show you, those voxel coordinates are essentially these ix, iy, and iz, and we can essentially, so there's a function in vex and even a node in VOPs, which is called a volume index to pause. So this takes a vector, which is basically xyz of the voxel index coordinates, and it gives us the current position of that index coordinate. Okay, so what in the world is the voxel index coordinate? Let me show you. So we have a node called VDB visualize tree, and this is really cool to investigate or diagnose our VDBs, our incoming VDBs. So I will just show you the active voxels representing as points. So this is the current active voxels right now that we have. Just going to remove the velocity field so we can see one. So that's points. And if I show you the geometry spreadsheet, this is points with index coordinates. So if I tick that on, it will give me an attribute called VDB IJK, VDB IJK vector attribute. So you can see it has some weird values in there. And essentially, what this is a coordinate system. It's like a position of the voxel in the grid, in the VDB grid. So if you didn't know, this is actually the voxel itself, these boxes. Okay. All right. So we know that we have like these index coordinates. Why can we use this in a logic, for our logic? If I'm just gonna show you real quick what happens is if we rebuild our VDB every frame. Okay, so this is the VDB every frame. So if you can see, if I'm gonna plug this into my VDB visualized tree, you can see that our VDB IJK, our index coordinates, it will start changing every frame. You can see. So essentially the point order in geometry terms is not consistent throughout the frame range. Whereas if you compare it down here, where we have the static VDB and we transform it, if you look over here, yes, the positions change, but the index coordinates don't change. You see? It's all static numbers. So that's really cool. Why is it cool? Because it's essentially like a point number, right? So how do we access that in a volume wrangle? We can get access to those just like in the volume VOP using these intrinsic attributes, which is the ix, iy, and iz. And those are basically these ix, iy, iz. Okay, cool. So let's do whatever logic we have here on this volume wrangle. So first of all, I'm just gonna put a string because the function that we're gonna use is volume index to position. And what it needs is the input geometry, a string volume name, and a vector voxel. And that's basically our ix, iy, and iz. Cool. So I'm just going to create a string. And I'm just going to put here a surface just in case. And I'm going to brute force hard code surface here. And our vel, which is, I think it's called vel. Just going to double check. Yeah, it's called vel. So I'm going to put vel down there. And we'll do the same thing. We do the time shift method, plug it there, and plug that on the second input. So I'm gonna do a whole frame here because I just want to do a backward difference for now. Cool. Then we get the position. So vector key 1, and that would be volume index to plus. Cool. And we're getting from the second input, which is 1. And what's the surface name that we're going to use, the volume name? We'll use vel because if we use surface, just keep in mind that we will be doing some resampling on our velocity volume. So if you do some resampling on our velocity volume, we can't use the surface field to get, you know, positions and stuff because we're gonna write onto our volume velocity field. So we need to use the vel field instead. Cool. So vel down there. And what are we gonna use for the vector voxel? So we're just gonna build that. I'm gonna call it index coordinate. So that would be ix, iy, and iz. Cool. Copy that, paste it down there, And that's our position for our frame before. I'm also going to get the current frame, which would be P0. We can use at P, I think, as well, but I've been doing this on my tests, so we're just going to do the same. So it's the same exact thing, the same exact syntax, except we're just changing the geometry to 0. Okay, cool. So now we're going to write onto our volume velocity field. So it's v at vel equals whatever math that we did. So the current frame, which is P0, minus the previous frame. We're just going to multiply it by the seconds, and done. So we're writing out our vel. I'm just going to, this volume still write to. I just want to be explicit and say that we want to write on our velocity, on our vel field. So yeah, just a little bit more optimized. Cool, so how does that look like now? I'm just gonna grab this guy and check our vector fields. Cool, so now we're seeing something awesome. It looks amazing. So look, have a look and see. So we got some twisting vectors here because our hammer is gonna be twisting. And look at that, just pure gold. That's just amazing. That's all working perfectly. Look at that. Zoink. That's some nice velocity vectors. Cool, so we're essentially packing up here. So now we've got some cool logic for capturing our velocity values. And that's essentially what we just need, what we need to do. If you can see on this subnet, it's the exact same thing. Oh, another thing, sorry. If you want to be a lot more optimized here, since this is just a point with a transform attribute, we can actually just cache this out. So I'm gonna make a temp1 temp x form. You can cache this out, save, and it's gonna be really light on disk because it's literally one point with a transform attribute. And what you want to do for the in-between frames, because we cached it, we can just use a time blend. And using a time blend on a single point is super light. So we're not gonna get any hit on our performance. So you can see it's so really damn fast. Cool. And you just plug that onto the transform attribute. And if you can see this, so where's my hammer? I'm gonna go in between values. You can see that we've got in between frames. You can see it's 20.1, 0.2, and it's still moving. It's moving correctly. So that's really cool. Okay. Because without the retime, we would have this whole steps frames. Okay. So if you decide to cache, and I would highly suggest you cache your transform point, put down a time blend after it, and it's all set and good. Perfect. So now we can just plug that here, and we can run the sim, and it's gonna be amazing. It's gonna look exactly the same as this beauty. No stepping and incredibly fast. So perfect. Just to let you know, I have made this into, packed this pretty much into an HDA, which I called VDB Rigid Collider. So I'm just gonna show you how that looks like. Let's show you how this HDA works. So you just put it down, and the first thing is it sets the reference frame to whatever the start frame of your play bar is in Houdini. The next thing you do is under the quick setups, you say second input template, and we'll recreate all the nodes that we usually use. So all these up here, and we plug in our animation through the null. So this is the null, and the time shift, the reference frame is set to whatever this value is, and the retime, the input frame range, is also set on the range of our play bar. It also automatically set the parameters of our extract transform and also our attribute promote. Also creates a file cache here for your convenience, because this is the best workflow that I like to use for this optimized collision VDBs. So yeah, so what we have on the VDB Rigid Collider, I'm just gonna quickly cache this. It looks exactly the same, I mean almost exactly the same as the VDB Collider, because that's where I took inspiration from. So we have voxel size as well, exterior band voxels, offset, all these things, the reference frame. But we don't have any options for the collider type. We don't have any options for these collision response as well. And if you check with the VDB Collider, it also has segmentation, which is really useful. We can implement this in the same way, but it might add some complexity. I still have to try, but that's the next thing that I want to do for this HDA anyway. So let's just run down what we have on our parameters. So we have backward difference for our velocity approximation set as default, but I also added central difference, so we can just have a look. We also added a trail velocity here just to visualize that. So we have central difference, backward difference, central difference, and forward difference. Just be careful, although central difference is really accurate, the problem with this method is, so we've been doing this time shifting, right? It basically creates a copy of the volume that we have. So basically we now have two volumes. With central difference, remember we have to use two time shifts. So one is the half frame before and half frame after. So now we essentially have three copies of our VDB. So that's the only drawback to this method. So that's why I just set backward difference as the default for now. Okay. We also have controls over the resolution of our velocity vector. So by default it's set as 2. So multiplying it by 2 on from the SDF resolution voxel size. And exterior band voxels as well. And this offset thing is the same thing as the VDB Collider. It just erodes or dilates our SDF. Okay. We also have the invert SDF here. This bindings is the default of the name for our pyrosolver. So if you put down pyrosolver, by default it accepts collision for the SDF, the name, and V for the velocity volume. So that's why I set those as default. You can use this for Axiom Solver as well. You just have to name this to a collision vel, and that's it. And it should work with Axiom as well. Cool. So yes, although we use this kind of method, we have access to the file cache and the time blend thing. On this VDB Rigid Collider HDA, we also have an option to, if I just plug this straight into the input animation, we can untick this use second input transform, and now it will just use, it will calculate everything inside all these extract transform within the HDA itself. So you can see all calculates it inside the same way as the VDB Collider does, and it all does the same thing, creates a velocity vector for us, as you see here. But the problem with this method that I find is because there's an option, if you untick the C-second input, there's an option to time blend. This time blend will create you know, the in-between frames, and it reads the geometry live. And this is what I want to avoid. I want to avoid reading, you know, the input animation live, because it will just slow down. It will just slow us down because it has to read, for example, if this was a really heavy Alembic file, it has to read those Alembic files, you know, on demand. So I wanna get away from that, and that's why I added this as a default. So I'm just gonna bring this to 1. So I just have this second input transform as the default and use the second input template for our convenience. And I think this is a much better workflow. It's a lot easier. It's a lot lighter. We don't have to read the input animation live on demand because we're just gonna be caching out that single point with a transform attribute onto disk, and that's what we want to time blend. Okay, and yeah, I think that's pretty much it. That's this HDA is going to be free for you guys. I will be updating this most probably to support this segmentation feature, which is really cool. We could probably use this kind of thing for, you know, like RBD, where we're not gonna use all of the pieces from the RBD, but we can maybe just, you know, the bigger pieces of the RBD, like the bigger pieces of the wall and stuff like that, and use that to transform our collision.